So now let's see what would be a robust version of the fact that lambda k is 0 if and only if G has k or more connected components. Well, one consequence of this fact is that if lambda k is 0, then since there are k connected components, there must be a connected component of size at most n over k. So when lambda k is 0, it is possible to find a relatively small subset of vertices that form a connected component. A robust version of this fact was proved by Aurora, Barak, and Storer. What they show is that it's always possible to find a set that is relatively small, provided that k is large enough, and whose expansion is bounded in terms of lambda k. Now, when k is equal to 2, what we get from Chigger's inequality is that there is a set of size at most n over 2, and whose expansion is at most the square root of 2 lambda 2. So we might be hoping for something similar where 2 can be, sort of these 2 and these 2 can be replaced by any k. That in general, if lambda k is small, we can find a set of size at most n over k, and whose expansion is at most the square root of some constant times lambda k. This does not quite show this result, but the upper bound on the expansion is if delta is a constant, is within a constant factor of what we get from Chigger's inequality. The upper bound on the set is quite a bit worse than what we could hope. It's worse by a factor of n to the delta. But this result has been very useful in working on the so-called small set expansion problem, which in turn has been studied very intensely by the complexity theory community because it's very related to the unique games conjecture, which is one of the outstanding open problems in complexity theory. Now let's see another way of getting a robust version of what the fundamental theorem of spectral graph theory says about lambda k. And towards this objective, let's define a generalization of the notion of expansion. In the case of expansion, what we're looking for is a partition of the set of vertices, such that if this is S and this is V minus S, and S is the smaller side of the partition, then we want the expansion of S to be as small as possible. In this problem, we're going to look at any k disjoint sets, and then we want the worst expansion of those k sets to be as small as possible. Notice that if we look at the case k equal 2, what we're looking for is two disjoint sets of vertices, all having expansion as small as possible. But then one of those two will have to have size at most n over 2. And so this is the same as looking for a set of size at most n over 2 with expansion as small as possible, which is the standard expansion problem. In the standard expansion problem, the expansion is 0 if and only if the graph is disconnected. In this more general problem, the order k expansion is 0 if and only if the graph has at least k connected components. Because for this parameter to be 0, it must be possible to find k disjoint sets of vertices, each of them having no outgoing edge, so each of them being disconnected from the rest of the graph. Which means that the fundamental theorem of spectral graph theory can be stated as saying that the order k expansion is 0 if and only if lambda k is 0. Now let's see some examples. Suppose that we have a graph whose eigenvalues are this sequence, ordered from the smallest to the largest. Now, just by looking at those eigenvalues, we can see that the graph is going to be disconnected. Notice though that the third smallest eigenvalue is rather large. Now this is the graph for which these are the eigenvalues, and although we can find that the expansion of the graph is 0 because it's disconnected, when we compute the order 3 expansion of the graph, that's very large. This is the 3 partition of the graph that achieves the minimal order 3 expansion. Now this is a graph where not only the second smallest eigenvalue, but also the third smallest eigenvalue are very small. They're about 1 over 20. And this graph has a cut of small expansion, just divide the cycle into two equal size parts. But it also has a cut of small order 3 expansion, just divide the cycle into 3 equal length intervals. The expansion is only 1/6. And indeed, it is possible to prove a Chigger-like bound for this order k expansion. So this order k expansion is small if and only if lambda k is small, with the same quadratic loss that we have in the standard Chigger inequality. And this upper bound is proved constructively, so that if you have the eigenvectors of lambda 1 up to lambda k, you can find k disjoint sets, each of expansion at most order of k squared times the square root of lambda k. It's also possible to show that the order k expansion is at most the square root of lambda, say 1.1 times k. This could be any constant arbitrarily close to 1, with an extra loss of square root of log k instead of a loss of order of k squared. So if I give you lambda 20, which is small, and I give you the 20 eigenvectors of lambda 1 up to lambda 20, it's possible to find 17 sets, all of very small expansion. I will just make a quick comment on the way those results are proved, which is that when we have the proof of the Chigger inequality, we prove it by analyzing an algorithm that, given an eigenvector of lambda 2, finds a cut of small expansion. Those upper bounds are proved by analyzing an algorithm. The given k eigenvectors will find k sets all of small expansion. And this algorithm is somewhat similar to algorithms that are used in practice for clustering, which work in the following way. So suppose we're given the eigenvalues lambda 1 to lambda k of the Laplacian and some corresponding eigenvectors. And in fact, the algorithm will work even if those vectors x1 to xk are not the eigenvectors of lambda 1 to lambda k, but are just orthogonal vectors of small Rayleigh quotient. So given those k vectors, since each vector is giving us a real number associated to every vertex, the k vectors together are giving us a k tuple of real numbers associated to every vertex. And we can think of this association as defining a mapping of vertices into a k-dimensional space. Just as in the proof of the Chigger inequality, we could think of the eigenvector of lambda 2 as defining a mapping of the vertices into the real line. Then those algorithms that seem to work well in practice just apply geometric clustering algorithms to this embedding. K-means is typically applied. And empirically, those algorithms seem to find non-expanding sets. To visualize what such an embedding could look like, here is what the embedding would look like if we take a random graph of about 100 vertices that has been generated by just arbitrarily dividing the vertices into 3 groups, and then putting edges with probability 20% within a group and with probability 2% between different groups. Then we computed the Laplacian matrix of this graph, and the eigenvectors corresponding to lambda 1, lambda 2, and lambda 3 for this matrix. The eigenvector for lambda 1 is just all ones, so it doesn't give any information. And then we use the eigenvectors of lambda 2 and lambda 3 to get this drawing. So the way we got this drawing is that for every vertex v, we look at the entry v in the eigenvector of lambda 2, the entry v in the eigenvector of lambda 3. This gives us 2 real numbers, and those 2 real numbers are the coordinate of the vertex in the drawing. And as it happens, the drawing tends to concentrate the vertices into 3 regions, and the vertices that get packed together in this drawing are precisely the vertices that we chose to randomly connect with high degree. And the vertices that end up being farther away are those that we connected randomly with low probability. So in random data that has a planted clustering, the clustering will be sort of apparent in the drawing, and just any algorithm that tends to put together vertices that are drawn close by will discover a good clustering. And in fact, this kind of analysis is doable with matrix perturbation theory methods, and it has been known for a while. But the higher order Shiger inequality that I mentioned before gives a worst case analysis that applies to every graph. It shows that for every graph, after you create that k-dimensional embedding, it will be possible to find k non-expanding sets just by putting together vertices that are nearby in the drawing. Although in our analysis, we don't use k-means, but we use a different geometric algorithm.